It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming You a Nice Coffee.
Hi guys, how you doing? Today I'm going to be going through equilibrium concentration calculations. So for each of the equations that I'll be looking at, and I'll be doing 4, down the bottom here I'm going to write the Kc expression for this particular equation. So for this one we've got some sulfur dioxide with oxygen giving us sulfur trioxide. So I'll start off by writing here the Kc expression. So Kc is equal to the concentration of our sulfur trioxide squared over the concentration of our sulfur dioxide squared times by the concentration of our oxygen. Okay, so we'll keep that in mind as we go through and do our calculations. But what you can see up here is we've got 3 moles of sulfur dioxide in a 500 ml reaction vessel. So initially over here what we're going to do is I'm going to put 3 moles, but it was in a 500 ml reaction vessel, so we're working out concentration here. So 3 over 0.5 is going to give us a total of 6 moles per litre of sulfur dioxide that we started with. And we started with 5 moles of oxygen, so 5 over 0.5, okay, gives us 10. Initially of our sulfur trioxide we had 0. It then says at equilibrium there is 2 moles of sulfur trioxide present, so 2 over 0.5 gives us 4. So what we've done here is we've added 4. So what we do is we then have a look at the molar, the stoichiometry in the equation. So over here what we've got is 2, 1, 2 stoichiometry ratio. Okay, so we need to keep that 2, 1, 2 ratio through the middle here. So to get from 2 to 4 we multiply by 2, so the number we must have in here must be at 2, and it's actually negative because we're losing our reactants. Okay, and over here we're going to lose 4. Okay, so we've kept our 2, 1, 2 ratio through here, and because we increased our products over here, we started with nothing, and at equilibrium we had 4 moles per litre, we've gone up by 4 moles per litre. So our reactants, SO2 and O2, must have decreased, so this one decreased by half of it because it's a 2:1:2 ratio, and this one increased by the same amount. Okay, so now we can get our equilibrium concentrations. So here we've got an equilibrium concentration of 8 moles per litre, here we've got an equilibrium concentration of 2 moles per litre. So if we want to calculate our Kc value using our equation over here, it's the concentration of SO3 squared, so it's 4 squared over the concentration of our sulfur dioxide, which is 2, so it's 2 squared, times by the concentration of our oxygen, which is 8. So if you put that in, you get 16 over 32, so our Kc value is 0.5. Remember, no units because the concentration in moles per litre cancels out for top and the bottom. Alright, Kc value of 0.5 tells us that the reaction is really incomplete, favours the reactants. Okay, so we've got more sulfur dioxide and oxygen in there. Okay, so that's the first one. Next one I'm going to look at is this reaction here between hydrogen and nitrogen to give us our N2H4 molecule. So again, down here what I'm going to do is write our Kc expression. So it's our concentration of N2H4 divided by concentration of hydrogen gas squared times by concentration of our nitrogen gas. Okay, so up here what we've got is 12 moles of hydrogen gas mixed with 9 moles of nitrogen in a 3 litre container. So for hydrogen over here we've got 12 moles in a 3 litre container, so that gives us a concentration of 4 moles per litre. Here we've got 9 moles of nitrogen in a 3 litre container, gives us 3 moles per litre. We started with 0 moles of our N2H4, and it says there is 8 mole of hydrogen gas at equilibrium. So at equilibrium we've got 8 over 3, so that's 2.67. Okay, 2.67 moles at equilibrium. So what we do now is we look to go from 4 to 2.67. We've lost 1.33. Okay, so always start by putting the values you've got from your question into your table here. Draw this up with your initial go-to equilibrium. Get this initial value here based on the one that you have an equilibrium value for and an initial value for. Then calculate your others using the mole ratio. So it's a 2:1:1 ratio. So these ones here must be half of this one because it should be 2:1:1. So half of that we're going down by 0.67, and here we're going up by 0.67. So our equilibrium concentration here is 0.67, here is 3 minus that, so it's 2.33. Now we've got our values, we put it into our Kc expression, so it's concentration of N2H4, which is 0.67, over our concentration of hydrogen squared, which is 2.67 squared, times by our concentration of nitrogen, which is 2.33. Put that into your calculator and you get a value of 0.04. So that's a really low Kc value, again, highly favouring the reactant, not much product there at all. Okay, so those two are kind of similar, they're kind of your basic ones. Make sure you can do those first and then you can start tackling some of these harder ones. So the first one I'm going to look at is this one here, synthesis of methanol. Now, because this is a little bit harder, and to make sure we're focusing on our just doing our Kc calculations, I've given you the concentration here in moles per litre. So just make sure when you get to the exam that you actually read the question thoroughly and read if it's talking about number of moles in a particular container or if it gives you the concentration straight away. Okay, so in this one here it says at equilibrium there was 1.56 moles per litres of methanol. So 1.56 moles per litre of methanol and 1.03 moles per litre of carbon monoxide. So 1.03 moles per litre of carbon monoxide. What we are trying to calculate is this value here, the concentration of our H2. So Kc is the concentration of our methanol over the concentration of our carbon monoxide times by the concentration of hydrogen squared. Okay, so we're going to use that value and rearrange it. So we get told up here the Kc value is 14.5. Okay, so we go 14.5 equals concentration of our methanol, which is this one here. So it's 1.56 over concentration of carbon monoxide, which is 1.03. 1.03 times by the concentration of hydrogen squared. So we rearrange our equation and we get hydrogen squared equals, so it's down the bottom here, so we flick it with this one over here. So it's 1.56 over 1.03 by 14.5. So all you've got to do is swap the position of those two. You'll get a value for that. You square root it, okay, just to get the concentration of H2. So if you work that out in your calculator, do the square root of it, you get a value of 0.323 moles per litre. Okay, so in this case, because the question is actually asking us to calculate the concentration, you must put some units in. Notice in the last ones when we were calculating the equilibrium constant, we didn't need units, we didn't need them. Okay, but in this one, we need units in here of moles per litre. Okay, so that one's getting a little bit more tricky. I'm going to do one more which is even a little bit more involved. Okay, so the final one we're going to look at here is an equilibrium between N2O4 and nitrogen dioxide. This is another one where you can look at the colour change, because nitrogen dioxide is a brown gas and N2O4 is colourless. So the position of your equilibrium is determined by, or can be determined by the colour of your gaseous equilibrium. Okay, so what we've got up here is a Kc value of 13.6. Alright, I'm going to write the Kc expression down the bottom, same as I have before. So Kc is equal to the concentration of NO2 squared over N2O4. Okay, now I've got 2.6 moles of NO2 at equilibrium. So at equilibrium we've got 2.6 moles. Okay, and what we said there was none initially. Alright, so up here's none, we know that we have to add 2.6. Okay, now the mole ratio here is 1 to 2, so we know here that we must minus 1.3, alright, to keep that 1 to 2 ratio. Okay, so the question is we need to work out the equilibrium concentration here and use that to calculate our final answer here for our initial concentration. So if we put our value of 13.6 into our Kc expression, we've got concentration of NO2, which is 2.6 squared over concentration of N2O4. Okay, so if you rearrange your equation, okay, you get concentration of N2O4, alright, because this one's on the bottom, you just swap these two, is 2.6 squared over 13.6. You end up with a concentration here of 0.497. So down here our equilibrium is 0.497. So what happened here is we had a number here, x, alright, x minus 1.3 is equal to 0.497. So if you add 1.3 to both sides, you cancel that out, and you get a value of 1.797. So that's our equilibrium concentration of N2O4 in moles per litre. Okay, hope this has been helpful. I know I've gone through the calculations reasonably quickly, but my advice is to go back over them, pause it before I start each of the calculations. Okay, try it for yourself and then check against what I've done. If you want any more help, check your Pink Chem Essentials booklet, or ask me and I've got some more help I can give you as well. Okay, thanks guys.